Okay, so welcome everyone. We start today's session. First of all, anyone has any question from yesterday? Yep.
Yeah, so for the economic analysis, are we, like for example, I've seen the economics, like they calculate the pre-tax NPV, the post-tax NPV, they include the inflation in the economics. So we are not.
We are doing a very simplified analysis. One
Okay.
problem that I found, I maybe will show you the exercise that I have planned for that section. Really, what we are giving here is a very simplified methodology to calculate cost, okay, and to calculate cash flow. In real life, you have to. Every company has its own method, and every time you have to. The calculation and the estimation of the cost is much more complicated than we are showing here. Okay, but this is very simple and also explains, kind of illustrates the illustrate how is the method. Okay. So let me maybe show you. So the next set, I hope to publish this. Still, we need some data. Some data is missing that we are going to get from Dr. Eter Madar. But so the first exercise is to practice what you learned from the lecture of Professor Golan, okay, on calculating total recoverable reserves. And you have the same equation that you were using during the class to calculate a very simplistic equation, but we want to take what happens when you have uncertainty in the parameters. And each parameter has a triangular distribution and is given by this table here. You have a maximum, a minimum, and a mode. And the second example, it's at a very, what we have taught here in class, maybe some of you had a better, those of you especially who are taking petroleum economics have more complicated methods. But here we are saying that you have a field called the Taylor field. The name might sound familiar to some of you. And we have two methods to develop this field, or two approaches. We are proposing two different production systems. So one of them is with a circular type Sevan platform, that you have the subsea templates, you have the well subsea, and then you have some flow lines that take the production all the way to the FPSO. And then from there you have a tanker that is shipping the crude all the way to the market. And the gas and the water is being re-injected. So that's one option of development, and the other option that you have to take into account is what happens if we send the production straight onshore. What happens if we don't build any FPSO? We just put some multi-phase boosters. That distance is quite long, okay? The field is 80, 90 kilometers from shore. So what happens if you install boosters and then you ship and you do all the processing in an onshore plant? In that case, you can also sell the gas, but you have some issues that you have to consider. So I have given you, and I have tried to find approximate costs for some things, for some units, okay? And really if you want to do it properly, or if you want to do it more detailed, you have to go and take into account many things in the cost, okay? In the cost of drilling, you have to do a proper duration of days. Maybe you have some days you are installing equipment, some days you are just doing testing on the well. So that part is being neglected in a way here. That cost estimation is being neglected. But I think you have enough information from yesterday's class to solve that exercise. Okay, and as I encourage you, as always, to if you want to think that the input is not correct, or if you want to do something more advanced, or if you have another way to solve it, also that's encouraged. Okay, so we are missing this cost for the onshore operating plant, but I think that's we obtained the value today. That's $180 million. Okay, and you're going to get that exercise tomorrow. But I agree, there are some things that we didn't cover. Also, the interest rate of return. We also didn't cover those concepts, and also we didn't cover what he was the net present investment. But really, for the usage that you're going to have, you have to be aware maybe that they exist, but it's not the most important. One of the most important factors to take a decision is the NPV of the project.
Yeah, so like if you want to incorporate the tax in the economics calculation, so should we just subtract it directly, or should we calculate the taxable income first and then subtract it?
The tax is not included in this exercise, okay? And tax, as I told you, approximately that's done on a company basis, depending on the revenue of each company. But really the details, we're not going to include it here because it's a bit more complex, but at the end you get the idea. So those of you who want to do tax and want to see the details of that, I recommend you to go to this course in petroleum economics. Yeah.
How about the depreciation?
Also, yeah, you take. You can make it as complex. You can propose that you want to include depreciation of the equipment here, or you want to include, for example, maintenance. That we are trying to compound all of that some kind of in an OPEX value. Okay. But you if you want to do it more advanced, you are welcome to do it. Okay. So that's the comment. With any other question? Sorry, from yesterday. No? Okay. So the topic for today, we're going to shift a bit away from field development. Okay, to talk about. But I recommend you to read I have put the first chapter of one book, this book that I showed you before, Exploration, Hydrocarbon Exploration and Production. And I recommend you to read that chapter, and I will try to upload some other chapters later this week. And the way we are going to do that, there are some things that I could be talking to you and give you just kind of a boring lecture, a lot of text and slides. But my idea is that you go and you read at your own pace at home, and then we have here a session that will have some kind of that has some questions to challenge you and to check that you have actually read the material. Okay, so I'm planning to have that session. We hope maybe at the end of next week or the week above. So you be ready for that. I will just let you know that you have to come ready for class. And of course, maybe to give some motivation, we say that we are going to put you in groups, and the group that wins, they are going to get some 1 point or something for the exercise. But I will let you know. Okay, so the topic for today is flow equilibrium. Okay, and actually, why is flow equilibrium important, or why are we having kind of a separate discussion? I'm planning that this will be maybe a 1 or 2 classes discussion. And it's very important because that tells you what is the performance of the whole production system. That allows you to calculate the performance of a production system. Or if you can summarize that, that's also in a way the performance of the field. And performance, really, if you see it from a macro perspective, or if you see it from a helicopter view, that has only to do with rate. How is the rate going to be versus time? But there are many other factors that are important to look at in a production system. Like you want to see, for example, the pressure and temperature distribution. Those are relevant, for example, for flow assurance. And to see, for example, how they are declining also in time. So pressure and temperature changes in time in the system. So let's start first. How many of you have taken any course in, or you know how to make hydraulic calculations in pipes? Pressure drop calculations in pipes? 1, 2, 3, 4? No more?
Yes, there are correlations.
No, not to go that complicated. Just single phase. Have you ever calculated pressure drop due to liquid flow in a pipe? Fluid mechanics. Okay. So 3, 4? Okay. Well, I'm going to have a bit of a tough work, but okay. So let's first put our preferred drawing of a production system. We have our well in a very simplistic way. We have our reservoir, and then we put here, we are neglecting all the other equipment that we have at the surface. All the other, remember, a well is an arrangement of valves. And then you have, let's say, if we want to make it, that's the seabed, and then that goes to a separator that is on top of a platform. Okay. And really, if you see at this production system, it has, what can you say that is the thing that maybe doesn't change, or the thing that all the time, no matter what, it remains the same? if we are looking at that at a certain depletion stage. Okay, we are, let's say that's a magnifying glass, and we are looking at that at a certain depletion state. Okay, there is one thing that's not going to change, and I told you that's going to be our reference. Okay, every time our anchor in the production system, what is that? The separator. Okay, if we want, the things are changing, you know, times we feel like we don't know where we are losing our identity, we all the time look at the separator. The separator, there is someone here, a control engineer, that is all the time making sure that this stays at a constant pressure. Okay, separator pressure. But if we look at a certain also depletion stage, if we make the analogy also to a tank system, what is also constant here? The pressure inside this tank, okay, the average pressure inside. If we say that this is an analog to, I think we had this picture before, right? So we had one restriction that was the reservoir, we had one restriction that was the tubing, and we had one restriction that was the pipeline. And at the end we reached this constant pressure. Okay. The pressure that you have, if you're saying you freeze the reservoir at a certain depletion stage, okay, then you can say that the reservoir pressure is also constant, or it is also fixed. Okay, so these two are what we call boundary nodes in our system. Boundary nodes. Of course, this boundary node, the reservoir pressure, is going to change. If I now look at another depletion stage, or I take out material from this reservoir, that pressure is going to go down. But if we look only at a certain depletion state, that's going to be constant. So these are our two boundaries. So now if we want to see, or if we want to calculate, and here I have put one well, but in the most general situation, you have just a collection of wells, you have a collection of pipelines, you have a collection of flow lines, so the system is much more complicated. So what do we have to do to understand how the system behaves with flow? How is the flow and the relationship with pressure and temperature? So what you have to do is, you have to, or if we want to solve all the time, we just don't want to know, okay? We just don't want to say, like politicians, that they speak, but we want also to make calculations. Okay, so if we want to make calculations in the production system, you have to include models for each one of the parts. Okay, so you have models for, and actually we divide the models for, one is for the formation or the reservoir. And here, let me tell you here, we are looking at one depletion stage. So really it doesn't matter, we are just taking out of the picture the time. We are not saying that we are looking at reservoir simulator, but we are just looking at how the reservoir is going to behave. So at that particular depletion state, okay? So we have a reservoir model, okay, or something that represents the reservoir, that we know that has to be more simpler than reservoir simulator. Okay, then we continue, and then we have the wellbore, then we have the actual well, and then we might have multi-branch, we might have a lot of equipment on the well. So what do we need here to capture all what's happening in the well? We need pressure and temperature drop in conduits, okay? But basically we have almost flow in circular conduits, and we have some accessories, some of the many things that you have in the well. Okay, so we need pressure drop, pressure and temperature drop. First, in circular conduits, thank God, all of our casing, tubing, all of those sections, they are circular, okay? Or we might have sometimes annular, but we have circular and annular sections of pipe. Or we might have also flow through accessories, like let's say in the well, if we have a slotted liner, okay, so we have the flow has to pass from the formation through all of these small orifices, and that's also going to cause some pressure and temperature change. Okay, so we have flow in pipe, and we also have in what I will call accessories. Okay, and these accessories are restrictions. We can call it restrictions. We can call it slots. We can call it valves. For example, when you saw that the well below the surface has a subsurface, a downhole safety valve, okay? And passing, of course, through that valve, that's going to cause some pressure change and some temperature change. So valve. So that's here in the part of the well, okay? Then you have a very important element that we have. Why is so important the choke? Okay? Because as you said, the choke we can use to control. We can use to the choke is just removing energy from the system to produce certain rate. Okay? So it's introducing a very high pressure drop, and that's why we have to look at it separately. So we have a model for the choke pressure drop, or delta P and delta T in the choke. And after we reach the choke, what else do we have? So we can say in a very simplistic way that we have flow in the pipeline or in the flow line all the way to the separator. So what should I use there? What do I need to calculate also that flow in the flow line? You say it's the same that you said for the well, okay? It's a circular conduit. So it should be more or less the same equation that I'm using for the well, you have to use it for the pipeline. So we can repeat that. So we put here reservoir, that's well, okay. That's choke, and here we have pipeline. And we are not going to talk yet, we are going to have a separate section on networks, okay? What happens when we have multiple wells commingling. So now we're looking at one single well, so we can assume that the rate is the same. Then is pressure and temperature, drop calculations. In circular, and here we are almost sure that everything is circular sections of pipes, and maybe some accessories, okay? Maybe we have some restrictions in the way. Some, for example, you know that when the fluid passes through an elbow or passes through a change of direction, there is usually also an enhanced pressure drop, okay? So we say accessories. Maybe valves. We have some valves. You know that in the manifold we have routing valves to send to one line or to the other. So every time that you have to pass through that valve, you create some pressure drop. Okay, so to make the story a bit shorter, so did we take all of those models that really are equations? This is a set of equations. Okay, and we need one more thing. What else do we need? So we have some equations for reservoir, well, we have flow line, and we have choke, but what else do we need? Like you will say, someone whispered now that you use friction, okay? Do you need friction? You calculate friction in these expressions. What do you need to calculate friction? You need Reynolds, and to calculate Reynolds, what do you need? Flow rate, but before flow rate, so we have the flow rate, okay? Let's say that you know the well is producing certain amount of oil, but that is a volume, okay? So how do we convert it to, what do we need to calculate Reynolds number? Yeah, we need viscosity. So viscosity is a fluid property, okay? So we need something, a calculator that allows us to calculate fluid properties also in this system. So we have a set of equations for delta P, for delta T, and we have also something that tells me how the fluid is behaving. So any of you has any idea what do we use for that? Correlation. So that, but we have really, you already have taken some courses in petroleum, so you already know a bit more than that, a bit better than that. We have one method. What is, for example, to use this equation? PV equal nRT. That's ideal gas, okay? But that's really in a fundamental name, it's equation of state, okay? You can use an equation of state, but you can use something more complicated. Those of you taking the course with Golan, you put a set here, okay? Or you have to use something even more complicated. There are some other options. You have Redlich-Kwong. Okay, you have, what else do we have here? Peng-Robinson. Yeah, and others, okay? Or you can use some methodology that the oil industry is using, is kind of a tradition, is using for a lot of time. So what is that? The black oil model. Black oil model. And we are going to talk a bit about that, but later, not now. So after you have these things, of course, you have to have one more assumption, okay? Are we saying that this is changing with time or not? Are we going to assume, for example, that this well might be producing a slug that reaches to the separator, a liquid slug, and then gas, liquid, gas, intermittent operation? Or what do you think? We might have actually the two types of okay, so let's put that here. We can have a steady state analysis. Okay, that means that we are going to take any dependence with time. Okay? We assume that if there is any transient that's going to happen, it's going to disappear very quickly. Let's say I want to change the choke opening. I begin to close the choke. Initially, the pressure is going to fluctuate, but then it's going to stabilize up to a certain value. So we are only concerned not between the period of stabilization, between the pressure. Let's say that you have, let's put that here, you have a graph that has choke opening, okay, and you have here pressure upstream, the choke. Okay, let's put it in yellow. So the choke opening initially was at certain value. Let's say it was completely open at 1. Here I have 0. But then I change and I put it in another position very abruptly. Okay, close 50%. So what's going to happen with the pressure upstream the valve? First I had a very, let's say a low pressure. Okay, then when I had this, it's going to go up, maybe down, up and down, up and down, until it's going to stabilize at a different value, okay, at a higher value. So we are really concerned about these periods, okay, a steady state simulation. If you want to analyze what's happening and exactly model what's happening here, then you need another type of model that are transient models. Okay, and we are not going to look into that because really, if maybe we need a very small scale. Maybe that happens, that change in the choke opening happens in 1 minute. So you have really to make a small discretization. In this minute, you have to make the simulation, for example, every half a second. And do you think that's really, it's worth going through all of that work to, for example, do the analysis for the whole time of the field, for the whole life of the field? Do you imagine making a simulation for 25 years every half a second? Okay, it will be crazy. So that's why we go for this analysis usually in our production to calculate the performance of the field with time. This analysis, why do we use it for? Well testing, for example, or we can use it well testing, okay, to get well testing to get information about the formation, information about what we have in the subsurface by doing some transient, by getting some transient readings. We can also do it for flow assurance. If we know that, for example, remember that the separator is really, the separator has certain volume, okay? Let's say that in a very simplistic way, you have this level, you have some things in between that are improving the separator, and then you have two exits, one for liquid and one for gas. What happens here, it's used that it will reach certain amount of gas and certain amount of liquid constantly. But then what happens if you get a batch of liquid at the same time, all of it very suddenly? So you're going to have, the level is going to go up very quickly, and maybe you will have some liquid entering into the gas line. Or if you get a gas pocket, that's going to push the liquid away, and then you have the liquid is going to be very dangerously low, and then you have gas coming into the line. So for this kind of phenomena, this slugging, for example, you want to make a transient simulation. Okay, so that's so this package that I told you here, steady state analysis, the fluid behavior, and the set of equations, that's what you will have to use when you in your future has petroleum engineers or production engineers. That's a production system simulator. Okay, there are different approaches. For example, if you have a gas, or if you have a mixture, multi-phase flow, or if you have oil, people go and program all the equations and give you all the different options. So they give you at the end a package that you can use to perform your computations. Okay, we're going to look a bit. I think it's worth in this course to go a bit below and see what is the principle, or how this software works, so you have a better understanding, and at the end you are a smarter user. Okay, you are understanding what the software is doing. So coming back to pressure drop, okay, let's make a small analogy that I hope that everybody can understand. So let's do an analogy for available we don't want to go right away to look at the equations. When sometimes you look at the equations, your mind becomes a bit blurry, or you say, oh, it's very complicated. So let's look first at some graphical method, how we can represent these equations, and then we will go to the details, okay, to the equations. So the analogy, let's say that we have a pipe, a horizontal pipe. Okay, so how do you make it that you know that it's a pipe? Something like this. Otherwise, it's just a box, I guess. Okay. So you have P1 and P2. P at the inlet of the pipe, let's say that it's horizontal, it has certain distance, and let's say initially that gas is flowing through it. Okay, certain amount of gas. Single phase gas flowing through a pipe. Now there are different ways that you can make a calculation here, okay, in this simple pipe. So what is one way that you could calculate? If I get P1 and P2, what can I calculate from here? The rate, okay, with a model. So that's one way how I can make my calculations. So another way is that I give P1 and Q and the rate. So then I calculate how much pressure losses I have in the system, and I will be able to calculate P2, right? Or there is a third way that I get P1 and I get P2, sorry, Q, and then I get P1, right? Different ways, but everything is doing the same. If I have the equations, I can compute exactly that, okay? By the way, this Q should be in which units? Standard, okay? What we mentioned before. If you put here, how did we say, a chemical engineer, they're going to kick him away. If we put here a mechanical engineer, they're also going to kick him away. If we put a petroleum engineer, that's the only one that's going to stay, because he's the only one that is going to report that rate in standard cubic meters per day. Okay. So in general, okay, the pressure drop that we have here in this pipe is the total pressure drop, okay, is a mixture of three parameters. We have dP dx of friction, that means the pressure losses that you have against the wall. Okay, the fluid is going fast and is going against the wall and is causing some friction, some energy and temperature increase. Then we have some other type of losses that are hydrostatic. And we have also acceleration losses. And this X in this sense is referring to the direction and coordinate system along the pipe due to acceleration. That is due to sudden expansions and contractions in the pipe. Okay, but let's not go too much in detail just now. So now I want just you to make an experiment. Let's say that we keep P1 is fixed somehow. Okay, like these boundary nodes in our production system. Okay, we are saying that this node, we have one node that is upstream. Okay, from that node everything is coming out of that node, and we have one node here that the separator that is downstream. Everything is coming to that node. With this pressure, they remain constant. They are our anchor of the production system. So let's try to make the same analogies in this same pipe system. So let's say P1 fixed, okay, and I say now I'm changing the Q is changing. What is going to be the behavior if we plot P2? What is going to be the behavior of P2 versus Q?
Decrease.
Is going to?
Decrease.
Okay, who agrees with him?
P2 is the upstream.
P2 is the downstream. P1 upstream, P2 downstream.
We are changing the separator pressure.
No, just forget about separator. We have a pipe. We have somehow, we are fixing P1. We are keeping it constant somehow. You don't want to know how, but we are keeping it constant. So what's going to be the behavior of P2 versus Q?
Q is increasing, then
Q is increasing, so
then P2 will decrease.
every time, let's say maybe we can do some, if Q increases, so then the pressure drops in the pipe. We don't have hydrostatic, okay, because it's horizontal. So we only have friction losses in a way. So when Q is increasing, also the delta P is increasing. That means that for a very low Q, if I have no flow, what value should I get?
Equal to T1
P2 equal to P1, right? If I have no flow, the two pressures are the same. Now if I begin to increase, now P2 is equal to P1 minus delta P. And delta P is increasing with Q. So every time that I'm increasing Q, then actually P2 is going down. Is that clear for all of you? Yeah, very critical for what we're going to do next later in this session. What happens now? I'm asking, what happens if now I change and incline the pipe? Is this curve going to change how it looks like? If I say P1, P2.
The shape will be the same, but it will go down the P2 and
Okay, you're saying the shape is the same, which maybe makes some sense, okay? But also when I'm zero, when I have no circulation, what's going to be the value here at the axis? Is it going to be P1? Okay, it's going to be P1 plus this hydrostatic column, okay? This delta H times the density times the gravitational acceleration. Well, if it's gas, it's slightly more complicated. Okay, so this curve, we are going to baptize that like the available pressure curve. Okay, is the pressure that is available when we have a fixed pressure point someplace in the system, the pressure that is available for each Q that I'm testing in the system. How much pressure can I get from this system depending on how much I'm getting. Okay, and really if you think about it, you know, maybe not too much, but just to give you just a hint. What behaves like that in my system? If I lower the pressure downstream, if I put P2 lower and lower, okay, that means that I will get a higher rate. What behaves like that in my system? The reservoir. Okay, is that correct or not? In this system, if I lower this pressure, I'm all the time going to get more and more rate. So that's exactly what this curve is telling me, this available curve. If I lower the pressure at the outlet, while the inlet is fixed, I'm going to get more and more rate. Now let's go to the opposite. Now let's say that we keep P2 constant somehow. Okay, and Q increases. Also our case with the horizontal pipe. So how is going to P1 going to look like? It's going to increase. How is it going to increase? Like that? Okay. So why we want to make it curved, for example? Why do we want to make it like that? Why do you think I not put a straight line? Okay. It's because of this delta P is a non-linear function of the Q, okay? And this Q is non-linear. So that's why you get usually that curvature. Okay. But do you agree with that behavior, all of you? Let's say you have, again, we do the same experiment. We say P1, okay, is equal to P2 minus or plus? What did we say here? This one looked reasonable for you, okay? Pressure 2 at the outlet of the pipe is equal to pressure 1 minus the pressure drops. Okay? So for this one, we just use this equation up. Okay? We just now clear P1 is equal to P2 plus delta P. That means when I have no flow rate, again, this pressure is P2. Okay? But then when I begin to increase the rate, I'm going to get more pressure drop. So P2 is going to be all the time greater than P1. And this, I'm going to baptize this curve like the required pressure curve. Okay, and now I think we can take a break, 10 minutes break, and for the second part of the session. Okay, we come back to our discussion. So going back to our production system, that's really what we are analyzing. Going back to our production system, so here we have, let's say we have said that we have a constant reservoir pressure. Okay, we know that that's an average pressure. Actually, we know that in the reservoir the pressure is not constant, but you have a variation of pressure. You have high pressure away from the well, and then when you reach to the well, then it becomes smaller. It begins to reduce. Okay, but we are saying that this reservoir pressure is an average pressure of the near well area. Okay, we are going to talk about that a bit later. So this is going to be like my P1. Okay, and that's in a way we are looking at a certain one point in time or one depletion state. Okay, we can call it QP. So that's going to remain fairly constant. As long as we are not taking any material from the reservoir, that's going to remain constant. So what's going to be, if we put here a rate, how is going to be the behavior of PWH, wellhead pressure, flowing wellhead pressure versus Q of this system? Now I want to use the concept that I have just learned. How is going to be the behavior of this system of PWH versus Q? Is that an available pressure curve or is that a required pressure curve? Available, okay? So it should look like something like this, right? A very simplistic, not going into the details, not going into the equation, very simplistic. If you put here, you all the time lower the pressure. You have here some equipment that you can control the pressure. And you lower the pressure, lower the pressure, lower the pressure. You all the time get more rate, right? So that's exactly what this curve is telling you. Now, be a bit careful. What is this Q that I'm pointing here? What is this rate? I say Q. For our case, we're dealing with a gas pipeline. Okay, so in this case, Q, what it could be? I'm producing three main products from the well. Okay, Q oil, Q gas, or Q water. So which one of them? Usually, what we use is the preferred phase. If it's an oil well, I'm going to use an oil rate. If it's a gas well, I'm going to use a gas well. And how do I calculate? I'm assuming that the GOR is constant. Okay, if it's an oil well, so this is going to be, I'm going to use the rate of the preferred phase. Okay. And to calculate the rest, I usually, what is done is that you say that the GOR for all of the points in this curve, for all the oil rates and the water cut is constant. All of you knows what GOR is? Say yes. Who knows what GOR is? Yes, we know? Okay. And water cut? You know also? Okay. Great. So we use the rate. When it comes to multiple phases, that becomes a bit more complicated, but still we can keep the same principle. Now let's take a look at the other part of the production system, at the separator. Okay, that's a constant pressure, so that seems similar to what system? The required, okay, the required pressure. So if we take here PWH, right, at the same point, because you are splitting the system in the same point, PWH, and now we want to compute how the PWH looks like with rate, okay, the rate of the preferred phase. So how that's going to look like? Okay, that's going up, just the way we said. Now if you want to calculate the rate, the operating rate of this, if you see we have these two curves, okay? Now when we put them together, there is going to be one unique rate that that system is going to produce, right? We cannot have multiple rates. When we put the two systems together, when we put, so that's, let's put here one comment, that's required. So if you want to see like, you know, I'm not sure if an analogy is useful here, but this is what the separator wants, okay? The separator needs this pressure. And this curve is what the reservoir can give you up to this point, up to the wellhead. So you want to have a compromise when what he gives is the same that what he gives is the same that what he is receiving. So how to calculate the equilibrium? We call it the equilibrium flow rate. So we just superimpose the two curves. We have PWH, both of them are wellhead pressure, and both of them have the same rate. So we have what is available from the reservoir up the way to the tubing is available, and overimpose the required pressure curve. And what's going to be the equilibrium rate? Just the intersection between them. At one point, what the system is giving up to the wellhead is the same that what the system is requiring at the wellhead. So this point, this is the equilibrium rate. And this is the actual rate that the system is going to produce. Is that clear? Yeah? Now you can obtain the same solution if you just go and apply a bunch of equations and you try to solve them, all of them at the same time. But I think this is, it's kind of a more, I would say, lasting explanation that if you just solve the equation. Okay. Now, okay, what happens now if our system, let's say, what if, okay, a what if scenario, to see if you understood correctly the issue. So now let's say we take the well, okay, up to here, but now we include the choke, and then we say the choke is 50% open. How that curve is going to look like, the available curve, if we plot it here in the same plot. This we said no choke. What happens now if we put a choke, 50%, we put it in the system? How the curve should look like? It should go down, right? Because I have more losses. This delta P that I'm calculating now has one more thing, that is delta P of the accessory, delta P of the valve. So it should be something like this. One question, the value in the origin, should that change? That's when I shut in the well and I leave it and I measure the pressure. That value changes if I have a choke or if I don't have a choke? No, because I have no flow. Okay, so we say that's available also. But if we have, for example, 50% choke opening. Now you see, okay, Bilal?
But the choke is on the downstream side of the wellhead, so why this curve is changing? Because the restriction is on the other side of the wellhead.
The restriction is, this is the system that I'm choosing, okay? This is the system. That is reservoir, wellbore, and choke. Okay, so this system is giving me this curve,
Yeah,
the red one.
But from reservoir to the wellhead, there is no choke. And the choke is after the wellhead.
Mm-hmm.
So the second curve should
Well, yeah, depending how you call it. In this case, I'm saying that the wellhead is here, okay? It really should be pressure downstream the choke, if you want to be formal. Yeah, maybe it's not... you want to make another figure, that's okay. Okay, what Bilal is saying that you cannot call wellhead, to his point of view, is the pressure that is upstream the choke. So you cannot plot if we are what we are plotting here is this pressure. We should call it differently, right? Okay. So we okay. So we say one curve, and we call it pressure downstream the choke, DC, downstream the choke. And let's say that this is for 100% choke opening, and this other curve is like, yeah, you will say this is for, let's say, 80% or 50% choke opening. Now the pressure that I have here of the other system, the curve is going to remain the same because that only includes the pipeline and the separator. Okay. So as you see the choke, that's why you already got an intuition that I can regulate the rate, the equilibrium rate, when I'm regulating the choke, depending on what's the losses that I have in the system. So actually that's what the choke is doing. So I can use that approach, and that involves, if you think about it, to include the choke model, the choke pressure drop model in my equilibrium calculations, right? But there might be another way to do it. Okay, let's see. So that's this analysis is including, what if we include the choke? What if we exclude the choke? Okay, for this approach to calculate this curve, you need to have a choke model. You need to check a choke model for delta P across the choke is equal to a function of the rate, a function of the pressure upstream the choke, okay, etc. Now, what if we exclude the choke from our analysis? What if we say, okay, we have our well, then we have an empty space, something goes there in between, and now I have the pipeline, and now I have the separator. I get exactly what I had before, right? I get, let's call this pressure point, we say P wellhead, we can call it, and then Q. Then we have the available curve, and we have the required curve. And I have, this is my equilibrium rate. No choke. Now what happens if I want to produce this rate, a rate that is lower than Q equilibrium? You see the two pressures, they are quite different. I have more pressure than what I really need. So how can I bridge these two pressures? In that case, I have to produce a pressure drop that causes exactly this drop in pressure, okay, that causes exactly this, this delta P. So that has to be the delta P of the choke. Okay? I think someone is trying to come. Let's give him a... Okay. Okay. So if you see, that's another approach. We have taken the choke out of the picture, taking the choke out of the model, and we have said, what is the delta P that we need to produce this rate? And based on that, you go to the manufacturer, or you go to your table and say, I want to find a choke to put on my system that gives me this delta P for exactly this rate, Q choked. Okay. I'm going to find and look in the catalog or look in my program which choke I can put, so it will give me that rate. Now what happens if the other case, now I want to produce a rate that is higher, that is at the right side of the equilibrium point. What's going to happen in that case? Can I do it?
You need to pump or suppressor.
Okay, I need to bridge this, I need to supply to what I have available from the reservoir, I need to increase it so it will reach what I require from my system. So in this case, if I'm talking about gas, I can put a compressor, okay, at the wellhead. And in that case, exactly when I put was what Bilal was saying, that when I put the choke, then the two pressures are different. Okay, you have one pressure upstream the choke, this becomes the pressure downstream the choke, and this becomes the pressure upstream the choke. the two pressures are different. Initially they were the same because they had no element here. But when I put the element, now the two pressures are different. So these are two approaches, okay? We exclude the choke model, okay? And this is very useful for, this particular approach is very useful for when your model is not good enough. That usually happens with multi-phase choke models. They are not accurate enough. Or when you want to do design. You want to exactly to be producing a certain rate and you want to design your choke. So this approach is useful for design and for not so accurate models. Now the same analysis that I have applied here at the wellhead, I can do it really at any other position in the system, right? If we go to our production system, how can I do it? For example, can I choose any other point and have the same analogy and it will be exactly the same? For example, at the bottom hole, can I do that? Yes, I can do that. I can say that I have an equation that is the available from the reservoir at the bottom hole, and then I can calculate an equation all the way to that bottom hole from the separator and try to do equilibrium there. Okay, so when do we want to use equilibrium, for example, at the bottom hole or at the wellhead or in the middle of the tubing? So who decides where I want to do my equilibrium?
Depends what is your objective.
Okay, it depends what is your objective, where to do the equilibrium. Okay, for example, just in case I don't forget, because afterwards I have to complement the notes in class, so that's not so nice. Okay, where to do equilibrium? We have usually two main points. One of them is bottom hole. And that's done if I want to do, for example, boosting design. If I want to do, or other type of artificial lift. Or if I want to use that input to control the reservoir simulator. Or also you have at the wellhead, and that usually I use it if I want to do allocation, field design, or if you want to do condition monitoring. Okay. You can practically apply this concept everywhere in the system. So let's maybe, just to be sure that you understood the concept. What happens if we have this system and we select the point just at the separator? So what is let's now separate the systems. I separate, and I want to calculate the available pressure curve for this system. So what will be that? That will look something like this. P separator versus Q is going to look something like that, right? And now I do the required, that's available, and that's required. How the required curve is going to look like? Just constant, right? I don't have any pressure drop, I don't have anything. The pressure, separator pressure, is constant, is my anchor. So it's going to be like that, and that's going to be the operational point. So really you can choose whatever point you like, but there are two main points, bottom hole and wellhead, where we want to do this analysis. Is that clear? Yes? Okay, so now we go and try to put that in equations and try to see how do we work with equations. So we are going to look in more detail in the models of the system, and I'm not going to give you this, the purpose of this course is not going to give you go through all the models of all the different parts of the system, just to make you aware to use some simplified models and to make you aware how things are changing for all the different cases. So first, let's look at the first or the first part in my production system, which is the reservoir. Reservoir, and we are going to call it deliverability. So we have what we are doing here is, after you understood the qualitative concept more or less, we are going to go actually to use numbers. So we are going to look in detail. So the first component that we find is the reservoir. How many of you took the course Production Wells with the Professor Ashheim? Okay, so this part is going to be a bit repetition for you. But the reservoir, usually, how do we compute that? We compute with one thing called IPR. That might be an equation, it might be a collection of points. An IPR stands for Inflow Performance Relationship. No, it's not internal present return or anything. Inflow performance. Some of these values that you were asking, that you want to know all the definitions. Maybe there is something called internal present return or something. Okay, so we can have an equation or a collection of points. And really, what does the IPR contain? The IPR contains many things, but it contains the information about conditions away from the well, and that means about the boundary. If you have your well, okay, and maybe that well is competing with another well, so this well is affecting certain areas, certain area around it is being affected, and this well is feeling the boundary that is feeling is just exactly when it crashes with the other one. Or if, for example, you have a well and you have a fault at some place in the field, so the pressure, this well is affecting more or less that region, but you have an information on the fault when it gets into the fault. Okay? So it has information, this equation has information about the conditions away from the well, about the conditions in the boundary. For example, we have a seal here, so that's neighboring producers. Neighboring, how do you write neighbor? Neighboring producers. Another information that it has is how easy it is for the flow to flow through the formation, for the flow to go through the formation. So that gives you some information about the flow restrictions in the formation. Okay. And that means not only it doesn't have not only information about permeability, about the fluid properties, the viscosity, or about the, for example, density. It has also information about, well, this should be small k. It has also information about some other restrictions that you have, that is actually, for example, skin damage, damage close to the well. It has also information about if you have any fracking, or if you have any perforation, if you have any channels created in the well. So it has perforation or fracks. Flow restrictions in the formation and in the near wellbore. So we can say that's and also has something very important, that is the convergence effect. And that means that when we have our well and we have every time, let's say that the fluid is going from the boundary all the way to the center is converging. So every time if you draw some kind of area that the fluid has to go through, initially the velocities might be very low. Let's say you have the same rate, okay, approaching the well. So the velocities might be very low, but when you're getting closer and closer to the well, then all the time you have to go through a smaller area, through a smaller passage, so the velocity has to increase. And this increase in velocity also causes some pressure losses in the well. Like you can see from every typical pressure distribution, if we have the well here, it does something like that. Very dramatic, very close to the well, a huge pressure drop close to the well because of these effects and because of the convergence effect. And then you have that farther away from the well begins to be smoother. So it's capturing all of that, and at the end the IPR, what is it? It's a representation, or it's a model of the pseudo steady state of the well. And why I'm saying pseudo steady state, why I'm sticking this phrase pseudo, because it's what I told you. Every time if you have the certain depletion stage, okay, you have the well exactly at certain pressure, if you begin to produce even a little bit, the reservoir pressure is already changing instantaneously. Okay, so we are looking really, there is no pseudo steady state. Everything is changing all the time in the reservoir, but we have to froze that moment, to froze that particular reservoir pressure, that particular depletion stage, and that's the representation for that particular moment. Okay. And this is usually, for practical purposes, is usually an equation that tells you Q, that coming from the formation. As I told you, you could use here the preferred phase, oil, gas, or water. Okay, you use, for example, gas if it's a gas well, and then you use the OGR, or you use oil and you use the GOR and the water cut. And here you have the flowing bottom hole pressure. Okay, so that's usually what the IPR is telling me. And how can you, I forgot to bring a picture, so maybe we can find something very quickly on picture on the web. No, that's not. I have a picture, but it's a bit well, like looking like the internet doesn't want to cooperate, so we can maybe use this one. I'm going to take one picture from the Book of Golan. Okay. So how do we calculate, or how do we get this IPR, this information? How do we get this equation? Okay, and one thing that probably you have done on your engineering studies is to derive it analytically from a series of the equations of the reservoir. Okay, let me just, I think I have those ugly equations someplace. So how do we get IPR? We can get IPR either from analytical derivation, okay, and that's what I'm trying to get, that expression from here, but basically I'm using the partial differential equations of the reservoir. In this case it's a radial well, and undersaturated, I'm assuming that there is no change of phase there. Undersaturated. Okay, r is just the distance from the well. If we assume that there is a circular boundary, and r is the distance of any point in the well, and this is describing the flow, the fluid through the formation. That's the compressibility of the fluid, r and dp dt. And h is just, if we look at the top view of the well, but if we look at it on the lateral view, h is just this distance. Okay, we are assuming that it's just exactly a cylinder. And well, pi, you know what it is, viscosity and permeability. If you go now on that equation and then you apply some boundary condition, that's a partial differential equation. Okay, and then you apply, remember that to solve this equation we need also a boundary condition. Okay. And we have two kind of boundary conditions that are usually applied to this equation. One of them is fixed pressure. And when could we use fixed pressure, do you think? Those of you who took production wells, you have to help me to keep the class alive. When we have, for example, when you think that you are injecting, you have one well here, and then you have an injector very close to it. If you're injecting, so that's in a way that's trying to support the other well, that's trying to keep the pressure constant. So for those cases, you might use a fixed pressure boundary. If you have, for example, injection, some kind of injection. Or you also could have I think in class I forgot to write here. So you also have a no flow boundary. That means that reaches, for example, that's a fault, okay? Or if there is a neighboring well, then at that particular boundary there is not going to be any flow. So that's the other type of boundary that you could use. So you use that for different geometries, different types of well, different fluids. You can use saturated, non-saturated, whatever you want. And then at the end you obtain an equation. That's what I'm trying to find from this book. So they have the equation. If you want to see the details, you can go to this book, the book that I posted the picture on the first class, and you obtain where is it? Okay, one equation, something like this. That's of course that's okay. As an analytical equation, that's for radial flow. I think that's oil, assuming that the oil, there is only oil single phase in the formation. Okay, and here I hope you recognize everything: viscosity, oil volume. All of you know what BO is? Yeah? All of you? Who doesn't know who BO is? All of you? Sure? We are going to come back to this issue later, okay? Oil formation volume factor. Okay, that's LAN and that's RE. This is the radius of the wellbore. Radius, and this is the radius of the outer bound of the outer. And similarly, you can obtain for more complicated cases. If you want to take into account the pressure scheme, pressure drop, you can also put it in that equation. If you want to assume horizontal well, you can also derive it like that. If you want to put two phases, you have oil and gas, so you can also put it in that equation, and you get an analytical expression for all of them. The thing is that these equations are made based on assumptions. Okay, for example, that is homogeneous. all the properties around the reservoir. Usually you have changes in porosity, you have changes in permeability, you have changes also in the properties. Might be that you have a combination. Initially you have just single phase, and then closer to the well where the pressure drops below the bubble point. If you say again pressure versus distance, and then you have something like this. Okay. Maybe single phase here, and then from here you have two phases. Okay. So all of these equations, you can use them as a first approximation, and usually that's what people use when they do early field development studies, to calculate the productivity of the wells. But after that, what is another method that you could use for getting IPR? If you have the actual well, what do? You can test it, right? So you do a well test. So let's think about how do we do that. If we have, let's say, a well, okay, we have the perforations. Let's not put too more complications, just put the perforations. We have a well and a formation. So usually there is some wells, they have either already a gauge installed, a pressure gauge installed bottom hole, or you lower with we have to put our tubing, and we have to put our seals. So people lower in a wire the pressure transducer, okay, and then what they do, they just begin to test at different rates. Why not one rate only? Can I make just a test at one rate? Is it all the time like that, non-linear? Let's spend some more time on that discussion. So how the IPR looks like? How does it look like? So for liquid, for undersaturated oil, it is a linear relationship. Okay, PWF versus Q of oil is just a linear relationship, and that usually we can express with the equation Q equal to a productivity index times PR minus PWF. That's what we call this. J is the productivity index. Now for this case, is it enough with 1 point? If I put the well on test, I'm producing certain rate, I'm producing certain Q here, I measure the rate in the separator. Let's say that I have here, well, now I'm complicating a bit the thing, but I have here the separator and I'm measuring the rate, how much is coming out. So I have 1 point. Is that enough? What else do I need? What is this point here? Reservoir pressure, okay? So I need to have, if I make only 1 point, then I have to have reservoir pressure. How do I measure reservoir pressure? Just I shut in the well, I let it until it stabilizes. This pressure initially is going to change, it's going to begin to increase. Actually, I can show you, I have, maybe not for this class, but I have a picture of that, very nice. The pressure is increasing with time. Make here pressure versus time, and it's increasing until it stabilizes, and that's where my reservoir pressure is. What is the problem with this approach? Every time I close a well, the company doesn't get any money, so they don't like that. You go like production engineer, you say this point is very important, we need it for our J, we need it for our equation. Okay, how much? Okay, how can we do it? You have to close the well for 1 day or 2 days or 3 days, and then you're kicked out, and then another one comes in and say, okay, what do you need? I need, again, reservoir pressure, etc. Okay, now we go for other cases that are gas or saturated fluids, saturated oil. For those cases, then it's a bit similar to what we discussed already. It's curved, okay? And in that case, we are in a bit of a problem, because it's not enough only with shut-in and just 1 point, but usually, have you tried to tune one equation like that to 1 point only? No? I mean, we might want to do the exercise, but okay. So actually for these curves you need more points, so you need a multi-rate test. multi. So maybe we can put just a comment there. How can we make space? It's a single test. We can put here single point. And shut-in pressure. But here I need a multi-rate test. To be able to capture enough, and then it's another issue because I'm putting the well lower to what it could produce, and depending on the time, sometimes, as I told you, the stabilization of each point takes time. You change, for example, that's the bottom hole pressure versus time, and we put also in red, we put the rate versus time. You have initially one pressure and you have one rate, but then you change the pressure to another value, and the rate, if you increase the pressure, what's going to happen with the rate? It's going to go down, right? It's going to decrease, but maybe sometimes this period until it stabilizes. This period, that depends on the formation. Okay, what is the velocity at which the pressure changes propagating the formation? And sometimes this period for a well might be 1 day with very good productivity, 2 days, but some wells you have to pass months. For shale wells in the US, there has to be months for reach equilibrium. So testing each point is expensive. So we say another point, for example, another pressure going up. So that stabilizes, and then I have to do some more space. And then it drops again. So this is a stabilization period, or transient. We can say transient, or not. Let's not call it transient. Remember, all the time everything is transient in the reservoir. So let's call it stabilization period. Stabilization. Okay, and that's a challenge, and I try to do nowadays modern wells, they already have a pressure gauge or a pressure transducer at the bottom of the well, and you can have live measurements of this value. But that's a very expensive process, and people usually, production managers, they don't like to test the well. Okay, it gives you a lot of information, tells you how much potentially the well can produce, but they don't like it. So here there are some equations, practical equations that we use for gas and for oil. I'm going to continue just here. And that's the famous Vogel equation. I think you have heard the name before, I guess. So the equation looks something like that. Q divided by Q maximum. PWF divided by PR. Where Pmax is the value at the lowest bottom hole pressure, is this value here. That's Qmax. Sometimes called absolute open flow potential. Absolute open flow potential. That's Vogel equation, very popular, and that's what is being used in most of the oil wells. And you also have the gas equation, back pressure equation. And that equation looks like this, QG where N is all the time a value. N describes how is the flow in the porous media. If it's laminar, if it's turbulent, it tells you information about the regime of the flow inside the porous media, and it's all the time a value between 0 and 1. So you see here the problem. To use that equation, you have one unknown. Let's say if you want to tune that equation, do you know how to do it in Excel? You have a collection of points. Let's say that we have rate test results, well test results. Okay, and let's say we have reservoir pressure for a rate equals 0. Pressure, bottom hole pressure versus rate. Let's say that they allow us to make the shut-in test. Then you have some other values. You have flowing bottom hole pressure 1, flowing bottom hole pressure 2, bottom hole pressure 3, and Q1, Q2, Q3. Do you know in Excel how to tune this equation, how to find the coefficients C and N for the back pressure equation? Yeah, do you know? No? Any ideas how you can do it?
We can
Yeah.
take the log on both sides and then arrange the equation.
Mm-hmm.
We can plot PR square minus PW square versus QB.
That's one approach, but let's use maybe the solver that we'll have already looked before. Let's say that we program a user-defined function, like I told you. Program a user-defined function that is going to give you PWF versus Q. So for that you have to clear from that equation, you have to say Q to the 1 over N divided by C. All of that divided by C. PR minus that. And then square root of PWF. You can create one user-defined function like that, right? So then you can substitute, create here another column, and you say PWF calculated with my back pressure equation. You define some place here up in your Excel sheet. You define your input. You say C equal to an initial value and N equal to an initial value. Okay. And then you, for each one of these rates, you calculate how much the PWF is. PWF1 calculated, PWF2 calculated, PWF3 calculated. And then what do I have to use? The solver, okay, to change these two until these two are the same. But how do I make that? Remember that the solver doesn't like to have multiple cells. So how can I make that?
Make a relationship.
I can, let's see if that works okay. I can make another column. Let me just put that to the right. I can make another column called error, okay? And I say that this is the PWF measured minus PWF calc squared. And then here I make the summation of all of these errors. And then I can tell the solver, please solver, change C and N until this error goes to 0. And that's how I obtain my equation, my C and N coefficients from my data points. Maybe I'm not sure if I will cover an exercise about it, but I think it's good that you can practice. So I will maybe upload some data on its learning so you can practice, okay, and do it yourself. Because it's not the main purpose of the course, but that's what the many production simulators are doing. When you provide test data, like a table, they are trying to tune the coefficients on the equations that you have until you match the data, the measured, with the calculated. Let's take a break, another break, and we come back with, let's say, 15 minutes this time. Yep. I have uploaded in the folder of today's lecture an Excel file that I want you to work with that if you brought your computer here in class to do this equilibrium. So now that's on the side of the well, okay? So another comment is that that equation is usually done for the preferred phase. for the phase that you are producing mostly, and the other rates or the other points. For example, you have your IPR for oil, and the other are calculated like just with the GOR or the water cut, just a multiplier. Okay, that will be just Q gas is equal to GOR times Q of the oil, right? But sometimes it could not be the same, okay? The GOR and the water cut doesn't keep for all the points. What case might you think that might happen?
Undersaturated.
No, not saturated, just what could happen that the GOR of 0.1 is different than the GOR of 0.2?
Because you have the free gas producing and its mobility depends on this drawdown.
A simpler case, let's put a horizontal well, okay? Let's put we are producing from a very thin oil rim, and we have a very big gas cap. The level of this surface depends on the drawdown that I'm forcing on the well, the pressure that I have on the wellbore, right? So what happens when I lower too much this bottom hole pressure? Every time there's going to be one point in time where I'm going to get gas cusping. This gas is going to enter. And then that point might happen that GOR is not anymore constant, and that's where it's going to change. After it passes some critical PC, critical coning PWF. Okay. So that's one example that might be different. These changes that you're saying with saturation around the wellbore, that's actually changes that happen with time due to changes in reservoir pressure. Okay, when the reservoir pressure declines, then the pressure around the wellbore is changing. So all the time you have more and more saturation of gas, liberation of gas, and then of course the GOR in different times is going to change. Okay, but here remember we are looking just at one particular point in time. I think I had a picture, maybe.
But here the as we increase the drawdown, the PWF will be lower and there will be more gas saturation near the wellbore at low PWF.
But usually you can assume that the GOR remains the same for all the points. If you deduct it from the saturated, if you go to the book of Golan and Whitson, and you see the equation really doesn't, the GOR is, assuming that the GOR is constant. Okay, because the saturation around the wellbore is the same. Well, we don't want to go into too much detail on IPR, just to show you what modeling we have there, and there is also actually, if you want, there is a full course production wells working on that part. You have horizontal wells. If you have, well, maybe we want to make one last comment. That is, what happens when you have a horizontal well, for example? How do you define bottom hole pressure? Okay, so let's put that like a title. How do we define in a vertical well? It's very simple. It's just in front of the perforations, right? In a vertical well. In front of the perforations.
But if the perforations are very long.
But if the perforations are very long, let's say that we have, okay, and we have this is, I don't know, let's say 100 meters. So where are we going to take this famous bottom hole point? Is it going to be here? It's going to be here? It's going to be here? Where? Okay. Usually we take at the last point where there is no more intake of flow. When we have a complicated flowing structure, or flowing through a whole section, we take it to the last point where there is no flow coming from the reservoir, coming from the formation. It's like the same thing with the horizontal well. Let's say that you have the well, and then you have flow all along the well going from the formation to the well, and then you have a point where you don't have any more inflow from the formation, and that's usually the point where you want to put your bottom hole pressure. Okay? Please bear in mind that also if you do that, what happens? There is actually flow that is going through the in this case through the casing, in this case also through the casing. So you have flow also on top of the flow in the reservoir. You have flow in pipe, flow in a conduit, and the IPR is representing that fact. That clear? Is representing that phenomenon. When you have multilaterals, for example, you know that you have some wells that they have 1 or 2 or 3. So how do we deal with that case? We can make a compound IPR. We can say that the PWF is here and calculate an equivalent, okay, for all of these layers. But also we can say define for each one of them a PWF1, PWF2, PWF3, and then calculate IPR or test IPR for all of them. We will see maybe later when we talk about networks. But really you will see that this compound is taking into account I prefer just leave that for networks. That's okay. So in those cases, for the most general case, we don't need to use an equation, but we just use the table, a collection of points. Okay. That's for the particular case where the GOR and the water cut are a function of the PWF, okay, when they are changing for every point. For those cases, usually we just have a collection of points, and you see that we will see in the simulators that you can have PWF, QG, QW. By the way, is any one of you have used Prosper before? You have used Prosper PipeSim? No, Prosper. So in Prosper you have the option, you have IPR options, and you have a bunch of equations that a lot of people have been working along the years, and they say this one works better, no, this one works better. But you also can put your data, okay, and in that case it's just going to interpolate. And of course you have to have a lot of points, so it will give kind of a proper result. So IPR, would you say that the IPR changes with time? Now that we are looking at, at changes, let's say in depletion, IPR, does it change with time? If I plot, for example, I go to a well, okay, let's say we have a well here. We have some perforations. Okay, we have the tubing. Okay, and we are testing PWF, and we are testing what is going to be the behavior of the well, Q, PWF versus Q. So let's say at one certain time, let's say at the beginning of the year, we make a test and we obtain the following behavior. So what's going to happen at the later stage by the end of the year? The shut-in pressure first, if I close the well, the pressure will have a lower value, right? Because I have less material in the reservoir. So the reservoir pressure, PR of 1, let's say time 1 is lower than time 2. Okay? So PR1 is greater than PR2. But the IPR, you say it in general because the IPR is actually the curve. So the IPR is changing for each depletion stage. And sometimes, and we will see that sometimes, like for example for the case of gas, okay, you can assume that Q, C, PR squared minus PWF squared. And you can assume that what is changing, all the coefficients, if it's single phase, you can assume that C and N are going to remain constant with depletion. Or also, if we are talking about undersaturated oil wells, then also you can say that PR minus PWF. You can also say that J constant. And then it's nice because you have only one point. You need only to shut in the well, and from there you get the reservoir pressure, and then you substitute it into the equation for different depletion states. But what happens, let's say that you do that, and at some point you test the well and you get another C and another N, and it's still flowing gas. So what could have happened in the well? Something happened, okay? Something got damaged. Okay, maybe something got plugged. You got sand production that plugged your, if you're producing with a slotted liner, something happened that caused an impact, a negative impact in the productivity of the well. Okay. So that's the nice thing about, so in general, just to keep you, IPR changes with time. IPR changes with time, but for some particular situations, like let's say single phase gas or single phase liquid, you can assume, or usually the coefficients are more or less constant. For single phase and undersaturated liquid, the equation remain constant if and only if, I hope you're taking your notes because mine are getting uglier and uglier with time. So unless something has happened in the well. Okay. But really that's what we, coming back to the beginning of the course, that we said with the IPR you can calculate the potential, and the IPR is really what is changing in every depletion stage. And by IPR I mean the whole curve. Sometimes you can assume that only one thing changes, that is reservoir pressure, but sometimes usually the whole curve is changing. So you have to, each depletion stage, you have to know how is it changing. Right? Okay, so let's make now an exercise. You can, I hope you have brought your computer. So you go to the folder of today, classes and lectures, class notes and videos, the lecture of today, and you have this Excel file. So please open it. Oh, we are missing one thing before we go to the exercise. Well, so we talked a lot about the inflow, but now we have to talk about, if we want to make an exercise on equilibrium, what do we need? The tubing equation. Okay, we were missing that. So tubing equation. So you know that if we have, let's go to the extreme cases, we have single phase liquid, or if we have single phase gas. And remember that this tubing equation is only flow in a circular conduit. Flow in a circular conduit. That means almost like in a pipe. Single phase gas. Okay, so we have that the pressure drop along the pipe, okay, this is the direction along the pipe, total, is going to have three components: dP dx of friction plus dP dx hydrostatic, and acceleration usually we can neglect if there are no brusque expansions or contractions. Okay, so this one usually we can neglect. And hydrostatic, you know more or less, you have the intuition that that's hydrostatic is a function of, you already density, okay, the density of the fluid that is circulating, and that's a problem for gas. For liquid, the density doesn't change much with pressure, or doesn't change much with temperature, but for gas, it's a very strong dependence on pressure and temperature. So as the pressure is decreasing along the tubing, then you have a change of density. So that's affecting here, and also affecting the delta H, okay, the height, the difference in height. And then you have the friction pressure loss that is affected by the velocity, okay, or in a more general way, that's affected by the Reynolds number, that is density, velocity, viscosity, and diameter. Okay. So it's affected also if I have a very viscous fluid, I will have more losses than I have a less viscous fluid. And if I have a high velocity, then I will have more losses than if I have lower velocities. So I'm not going to go into all the details of that, but it's just that you keep the idea, and you have an idea, and the deduction, I'm going to put the whole deduction of the tubing equation in the class notes, okay, not in these notes, but in the some like additional information. So if you make a derivation going from basic principles to saying that the energy is conserved, and you have to subtract just the friction losses and the hydrostatic losses, and then you begin simplifying and kind of massaging this equation, you end up with this big expression, where it's saying that in a conduit you have point 1 and point 2, inlet and outlet. So the rate at standard conditions that is circulating through that pipe is equal to that expression. R, what is R? Universal gas constant. Okay, that M is the molecular weight of the air. TSS is temperature at standard condition. What is that? 15 point what? 5.6. You have been to the course of Curtis, I guess? Yeah? If you don't know that, you have to quickly go away or hide, because... And the standard conditions pressure? 1.025. 132. Okay, so you have those two, you have the diameter of the pipe, and you see a lot of, I think, Professor Golan, those of you who are taking natural gas, I think he made the deduction of this equation. Okay, we don't want to go into detail, but I will give you the document, and I just tell you, if you have some free time, please go and read through it and see more or less the assumptions that he's doing. But basically it's assuming that it's just single phase gas. You don't have any other phase, you don't have liquid, you don't have anything else. And it's also assuming that the gas is turbulent. Remember that you have the flow regimes in a pipe. All of you know turbulent, laminar? Who doesn't know turbulent and laminar? Yeah? Okay. Good. You saw that in kindergarten, I guess. So, yeah, so this, when you say that all the time the gas flow is turbulent, then it becomes only a function of the roughness and the diameter. Okay? And if you say that for tubings, usually that comes from the manufacturing mills, all the time there is a relationship between diameter and roughness. Okay, for a certain diameter, they already have a certain expected roughness. So if you put that relationship here, that gives you the relationship between the friction factor and the diameter. So you can make some simplification here. C is the deviation factor, and that is an average, and that's a bit tricky how to know, because remember that in the tubing usually we have a very high pressure here, bottom hole pressure, and a very low pressure, usually, let's say, if you're talking about gas wells in the US, might be 4 bar, and this value here might be, let's say, 150 bar, okay, 180 bar. So actually there is a big change in pressure, and there is a big change also in temperature. So really this approach, you have to find the right average. Or, like you saw in the course of Professor Golan, another option is just to discretize. You go by sections. You say, for example, I want to make 100 sections, and I assume that the temperature is more or less constant in each section, and then I apply the equation one by one. Okay. And this S is an elevation factor that the expression is given here. But at the end, what is important is that you get this expression, okay? That P1 is equal to a function of P2 and Q. And of course, you have two constants, a tubing constant and an S, that is an elevation constant. So we can use that equation actually for the simple case of gas to calculate what is the pressure drop across a gas well. Of course, doing some assumptions that the temperature, we have an average temperature and we have an average deviation factor. That clear? So remember, I can use that equation, even the same thing as I told you at the beginning of the class. I can put the outlet pressure and the rate, and then I'm getting what? The required pressure, the P1, okay? Or I can put P1 and the rate, and I can calculate the available pressure, right? Okay, and that equation valid for single phase gas. And nothing strange happening, okay? I think it's also for a constant inclination. Okay, constant inclination. If you want to apply it for, if you have different inclination sections in the well, you have a deviated well, then in that case you have to subdivide the wells in segments and then also do your discretization there, inclination. Okay, now let's go to our Excel exercise. Go to Excel. And we are going to practice a bit this equilibrium. Okay, so you have here a well called EVA number 3, and you have certain reservoir pressure. You have the C, that's the inflow coefficient from the formation, and N, the exponent. So all of that is what you're going to use on your IPR equation. Okay, and then we have some tubing coefficient and S elevation factor, and that's what you're going to use in your tubing equation. If you want to know, I have done here the details, how I estimated that, wow, why that has so many decimal points. Also, that's something else, something that you cannot do with Curtis, okay, put so many points. Okay, so here you have the values that were used to calculate, actually, to estimate these values here. So let's make that plot, okay? Let's first calculate the available curve. We're going to do our equilibrium at the bottom hole of the well. So let's write that down. One question, is it worth that I will put so many notes on the annotation, or you prefer less notes and because you will see the videos anyhow? Because writing notes takes some time. But I don't know what you prefer. If you prefer to have it on the videos or on the notes. On the notes, so it's worth that I write on the notes. Okay. Go to Excel, and now we are going to do single well hydraulic equilibrium. And I'm going to choose for that the equilibrium point is at the bottom hole. Okay, that means that if I have my gas well, and it's a gas well, so I have here, and I'm going to do it, I'm going to assume really that the separator is just very close to the well. Okay, that's typically in the US, that's what you have. You have single well, and each well has its own separator, and you can assume that the wellhead pressure is usually almost close to the separator pressure. So we can say approximation that P wellhead is equal to P separator, more or less. Okay, there is a distance, let's say 5 meters, something like that, but we are neglecting that. And we are going to put our point of interest, where we are going to put the magnifying glass, is going to be here, equilibrium point. Okay, you can be very creative, put the point wherever you want, but yeah, we have one equation for this system, and we have one equation for this system, so it's very natural to do it, to put it there, because there are two separate equations. Okay, so now let's put here IPR. So what should I give? Should I give Q Okay, I have reservoir pressure, so should I give Q to get bottom hole pressure, or should I get bottom hole pressure to provide Q? Bottom hole. Why bottom hole and not rate?
Because we know the range.
We know the range, okay? If you see the equation, okay, if let's I think that's worth to make a comment. Okay, if you see the equation of for Q, you have C of the reservoir, PR minus PWF squared and to the power of n. If you put here any pressure, for example, you probably this expression will be all the time defined. Okay, but if now you do the opposite, now you want to clear the rate. Let's say you want to clear the pressure. That's the square root of something, right? So if this something that is here is negative for any reason, let's say you assume a rate that was too high, that the well cannot deliver, then you have a square root of a negative number, and Excel is going to complain. Okay, it's going to give you an error. So that's why the suggestion of Bilal is very important, that this PWF, we use it like this, and this PWF, we know the range that it can be. It can go from reservoir pressure to a very low value. Okay, we can say almost atmospheric pressure in theory. So let's do that. And you see we got a, if we go to Alt F11, we have a repository of equations that we can use. So we have IPRQ gas, and that's exactly the equation that we need. Depends on CR, on N, on PR, and PWF, bottom hole pressure. So we use that equation. First we give a range for PWF, so that will be from reservoir pressure, and then we can reduce maybe by 50 bar. This minus 50, go by 50, 50, 50, okay, all the way to 4. Maybe we can plot it even up to 4. Now the Q, here I use the equation. Remember to call it, I can put just IPRQG, or I can just search for it, clicking on Fn. And what does this equation need? CR is here. I'm going to block it, because when I'm going to drag it down, I want it to be constant. Then N, then reservoir pressure is here, then bottom hole pressure, and bottom hole pressure is this value here. Of course, when I have first bottom hole pressure equal to reservoir pressure, I have no flow, so that's consistent. And if I lower here, I get all the time a higher rate, and the rate seems to be in million. So to make it also a bit more user friendly, I'm going to go format, scientific, 2 decimal places, okay, and now I know that it's from 0 to 3 million, more or less the range. So now let's make a plot very quickly. That plot looks nice. So we can call this IPR, or we can just say single well bottom hole equilibrium. Okay, and here we have to increase the size, put it maybe in 18 so you can read. And of course you see here that they are the opposite. We have pressure and rate. It has to be flipped. So to make that and not go inside, I just change here, click on the series and click up and say D and D and C, C. Okay. And so now I have to put the labels. Oop. Titles. And that value is in bar. And here we have the rate, so it's a gas rate QG, and that's in standard cubic meters per day. And we can baptize that. We can just maybe give a name to the series, and we say that that's the IPR. And it's going to put the name IPR someplace. Now let's go to the other equation, and in this case, remember, here we're calculating everything available at the bottom hole, and then I have to calculate required pressure from the wellhead, and I have to assume a wellhead pressure. In this case, they have wellhead pressure 35. We can use, they have 3 values, so let's see that. So this will be P2 in our equation, and we want to calculate P1. Okay. P2 is this one, so what is this P in? Okay, we have to calculate P1. I don't know why that part is here. So for that we use, let's see which equation is that. That equation is tubing to obtain, we want to obtain P1, right? So it's this equation here. And here we have to be careful. We see that we have a minus 0. A square root. Okay, it's inside a square root. So if this thing for some reason is negative, then we are going to have an issue. But I think it cannot be negative, right? Because you have just a sum. So that's what we are going to use. So how is that called? Tubing P1. And for tubing P1, what do we need? We need the CT that we have already estimated for this well. Then we have the S is here. Then we have the P2, and P2 is this wellhead pressure that is going to be constant. And then you have the rate, and let's try to see if we can use the same rate. So if you see, if the pressure at the top is 35 bar and there is no flow, the pressure at the bottom is 37. So the long height, let's see what is the length of the well. It's where is it? It's not here. Oh, it's in the elevation coefficient. Yep, I don't know. I think it was maybe 2,000 meters in that case. 2,500. Okay. Okay, you have 2 bar, and then I drag it down, and I get that if I'm increasing the flow rate all the way to 3, I'm going to get a pressure of 87. So let's put and cross these 2 curves to see how they look like. So I add a new one, and how do I call this equation? Tubing performance relationship, to be consistent. Okay, tubing performance relationship, and to be more explicit we can say required. And we are select here, that's X, so that's going to be the rate, and we select here the Y, and that's going to be the pressure. Okay, and you have the two curves and the intersection point. In this case, the well can produce quite a lot of rate, almost the maximum rate. The maximum rate is close to 3 million, so it can produce very close, 2.8, 2.9. How do we find this point, this intersection? You can take, if those of you who are good in mathematics, you're not good in mathematics? No? You should be, you are here, you are doing engineering. So you should be good in mathematics. You can take this equation. You can take one equation that is the IPR equation, QG equal to CR times PR minus PWF squared to the n. So you have everything here. You have PR, you have N, and you have CR, and these two are unknowns. And then you have another equation which is that Q gas is equal to CT, the tubing equation, 0.5. Okay, and this we are going to change now. This is WF, and this is wellhead. So you have in this equation you have the S and you have the CT, and you have the wellhead, okay, which is constant. So you have two equations with two unknowns. Those of you who want to play a bit now, if with mathematics later in the afternoon, you can go and try to assemble them together and see what is the solution. Okay. Those of you who want to do it in Excel, how do we do it? With solver, our dear and precious solver. So so that will be the intersection. We can create actually another point in between. Okay, we say it's in between these two pressures, I guess, right? Yep, it's exactly between them. So I'm going to guess with 100 bar. For that I drag that right here, and I drag that pressure here. So now I want to create an error column. Let me just get rid of all of that. And I say error. And we are going to remember that the error is going to be bar squared. And this is going to be only on this point. This value minus this value and squared. Okay. Then we say, and we come here to our dear friend, helper, and all the time supportive solver. Please go and take this cell to a minimum. Well, it's not going to help us if we don't give good instructions. Then we say changing this pressure, and we can put some help, okay? We can say it's already here. Make unlimited or unbounded variables non-negative. So it's going to try to guess with fine, great, and then we go to our, and that's exactly the equilibrium point, and that's exactly the rate, 2.86, the equilibrium rate. Okay. So let's take that figure. Maybe we can take that also. Oop. Any questions up to this point? No? Okay, and that's the intersection. That was 2.8 million, exactly this point here. 2.86 e to the 6 standard cubic meter per day. Now, what do you think is going to happen with time? With the reservoir is depleting. Let's say that we are keeping the wellhead pressure constant. We have a separator or we have a compressor. We have something that is keeping it constant. How this curve is going to look like with time, the blue curve, the IPR curve. This is IPR and this is TPR. You can do the experiment yourself, okay? You can just compute a new reservoir pressure. But the thing that you're going to have is for another time, you're going to have something like this. And for another time, as you, oops, not like that. Okay. So these are for different reservoir pressures, or that is the same to say for different times. P reservoir 1, P reservoir 2, and P reservoir 3. And in this case, we were lucky enough that the C and N remain constant along the life. But in general terms, you have to all the time to verify that. It might change, especially for oil and gas wells, it changes, and you cannot use the same expression. And you see that the intersection is changing also. What have we done today? Someone wants to make a summary? First, we made kind of a very simple analogy to curves, okay? We said we have an available pressure curve and a required pressure curve, and that can help us to represent and visualize complicated parts of a production system. Okay? This very simple concept is just a curve, but that really has inside it'll kind of represent all the pressure loss equation, all the IPR equation, and also helps to understand that you have an equilibrium. You have a point where the two curves actually, at that point, there is only one unique pressure. You have to have only one unique pressure. And how do you make the pressure the same? Just that the two curves, they have to intersect. Okay. Then we said, what else did we cover? That we can have two approaches. One of them was to include an element in the curve, for example, a choke, but then we have to have a model, and then we have to know how to compute it. Another way was to take out the complexity of the system and say, how much do I need, what element do I have to have there to provide certain rate? Okay, but that's useful only when I know the rate in advance. So that's useful for all of you. Begin to see now which case, which production mode, A or B? A, okay? So in plateau, you can use this calculation. Actually, you can compute exactly the delta P of the choke that you need to produce that rate. So that's the beauty of the plateau. I fix the rate and I can calculate my delta P. When I'm not in plateau, what do I have to calculate? The equilibrium point. All the time I'm going to be at the equilibrium point. And then I have to use solver, then I have to put one equation inside of the other, then it becomes complex. And this is something that you have to keep in mind for network. Okay, when we go later to network, it's the same thing. In network, if you give the rates and you can compute the choke, very easy. If then you have to find the equilibrium rate of the network, you have a fight, you have two wells that are fighting in the same pipeline, then you have to use solver, and then it's expensive. Then we saw about, okay, we began to look in more details about the system. We looked at the IPR and where the IPR is coming from, actually what it is. You may ask some reservoir engineers, they have no idea what IPR is. They say, we haven't heard that any place in our lives. For us production engineers and for you sitting here in the class, is very important. IPR is what represents how much the reservoir can deliver. It's only one equation, but it's very, very important. And it has, of course, its limitation, but it contains a lot of different phenomena, near well, maybe even flowing wellbore, a lot of different things is contained in that equation. And we saw some ways how do you model it. The most popular equation that we use to model, where they are coming from, and something that we have to take into consideration. Then to make a simple exercise, a single well exercise, I said, let's take the gas case. Okay, let's say reservoir with gas and also tubing with gas. We have a very simple equation, also very powerful. We took these two equations and we tried to find flow equilibrium using two methods. One of them is to having the two systems of equation, clearing Q and PWF, or graphically using the solver. So for next week, I'm going to continue with this. We're going to give you one more equation that is a pipeline pressure drop equation, so you can do one more exercise. That's for, not for this, but for exercise set number 3. Then we are going to talk about what happens when you have multi-phase flow. That's actually the most typical case is you don't have single gas, you don't have single liquid, but you have multi-phase. When you have multi-phase, things begin to be a bit tricky. And I think it's important that all of you are aware what to do in that case. And of course, then we're going to say what happens when there are changes with time. Okay, we're going to introduce some time changes, and we will do that not with reservoir simulator, but we will do it with material balance. Okay, just a simple tank model that we are taking material. Reservoir pressure is declining with time. We assume that the IPR doesn't change with time, and the only thing that you have to change in the equation is reservoir pressure. Okay. Any question? No? Okay, so see you next week.